Volcanoes that drink the deep. Arc volcanoes don't just sit above subduction zones by accident. They tap a plumbing system that starts with seawater on the seafloor and ends as steam in the sky. The surprise is how far that water can travel before it matters. Some is shed shallow, yes, but a meaningful fraction rides the slab down into the transition zone. When upwelling mantle or a rising plume intersects that hydrous storehouse, the result is magma that carries extra volatiles from birth. Watch how it changes the recipe. That's a volcano that drinks deep. Take dry peridotite and heat it. Nothing happens until it reaches a high solidus. Add water and the melting point drops by hundreds of degrees. Now small degrees of melt appear along grain boundaries, and those melts are enriched in water from the first drop. They rise because they're buoyant, and as they rise, pressure falls and more water comes out of the crystal structures into the melt, then into bubbles. That's where behavior shifts from gentle to violent. Gas-rich magmas fragment more readily. They don't ooze, they detonate. You can see the fingerprints in volcanic arcs around the Pacific. The Cascades, the Japanese arcs, the Andes, each chain owes its magma supply to water lowering the solidus in the mantle wedge. But the deep component shows up in how persistent and volatile rich some systems are. If transition zone domains beneath a given arc are well stocked, the melts feeding that arc arrive with more dissolved water. The eruptions tend to be more explosive, the gas plumes taller, the ash columns thicker. Not every eruption needs deep water, but when it's there, it tilts the odds. Hotspots complicate the picture. Many are fed by mantleplumes that rise from depths at or below the transition zone, punching through that sponge layer on their way up. If a plume's base spreads beneath 660 kilometers, it can warm and tap hydrous ringwoodite domains, scavenging water that's been stored for ages. Iceland is a case study in mixing. Plume heat meets a spreading ridge, while geophysical images suggest a conduit that intersects the transition zone. Hawaii, though basaltic and often effusive, carries variable volatile loads that hint at deep source heterogeneity. The message is subtle but steady. Plumes don't ignore the transition zone. They interact with it, even if the degree varies by case. On smaller, faster timescales, the effect shows up in magma ascent. Water dissolved in melt changes viscosity. It can keep magmas mobile at lower temperatures, moving through the crust rather than freezing. It also changes crystallization paths. Hydrous basalts evolve to andesites and dacites more readily, building magma reservoirs that are primed for explosive release. When monitoring networks catch rising gas ratios, swelling ground, and tremor, they're watching volatiles unbinding, water and CO2 leaving solution and inflating the system. The deeper the volatile budget, the longer such systems can cycle between recharge and eruption. We don't measure that deep budget directly. We infer it. Seismic attenuation beneath arcs points to small amounts of melt in the wedge. MT surveys image conductive ribbons that trace possible fluid-rich pathways feeding arc roots. Petrology reads the glass and crystals ejected in eruptions, their water contents, their pressure temperature histories. Every line points back to the same quiet truth. Volcanoes are not just heat engines, they are chemical engines, and water is their throttle. This isn't just about bigger eruptions. Water in magmas changes how volcanoes build and collapse. It promotes hydrothermal systems that alter rock into weaker clays, setting the stage for sector collapses and lahars. It creates acid fluids that eat conduit walls, widening pathways and destabilizing domes. A deeply hydrated supply keeps those systems active between eruptions, humming with steam, earthquakes, and subtle ground motion. In the wrong place, a city on a flank, a reservoir downstream, that background activity is the hazard as much as the blast. There's a sobering long view too. Over tens of millions of years, arcs migrate, plumes wax and wane, slabs stall and steepen. Each reorganization changes which parts of the transition zone are tapped and when. Some intervals deliver steady, moderate, volatile flux. Others line up the valves, a hydrated transition zone, a hot upwelling, a thinning lithosphere. The discharge is not a single event, it's a cluster. Decades to centuries of elevated eruptive activity regionally, or the onset of a flood basalt if conditions are extreme. The timing isn't ours to choose, it's set by plate motions and mantle flow. What about the myth of an ocean bursting from below? That's not how this works. There's no free sea ready to surge. The catastrophe is different and real. Volatile charged magmas that can turn a clear morning into night, shut down air corridors, contaminate water, and load the stratosphere with aerosols. The deep reservoir's danger is indirect. It makes more melt in more places more often, and it hands those magmas the gas that makes them efficient at reaching the surface and disruptive when they do. Stand on a caldera rim and feel that steady exhale, the hot breath carrying a little more water every hour than the last. That's the deep cycle speaking. A volcano that drinks the transition zone doesn't roar all the time. It sips for decades, then gulps in a week. When it does, the plume tells you how far down its straw reaches. Plates, friction, and the grease you can't see. Plates don't just collide. They grind, creep, and stall along contacts measured in hundreds of kilometers. What decides whether they lock hard or slip quietly comes down to what's in the tiny spaces between grains. Water, sometimes as true fluid in the crust, often as hydrogen in defects deeper down, changes that friction in ways you can't see from the surface, but you feel when the ground lets go. Follow a subducting slab beneath an arc. Near the trench, the downgoing plate drags pore fluids, sediments, and altered basalts into a zone where pressure compacts, heats, and squeezes water out. That water migrates up and along the plate interface, into the melange of sheared rocks and serpentinite that forms the plate boundary. Serpentinization is chemistry's softener. Olivine, plus water makes serpentine, magnetite, and hydrogen, lowering rock strength and adding what amounts to geologic grease. A boundary with more serpentine behaves differently than one that's dry. Farther down dip, temperatures rise and those hydrated minerals decompose. Fluid is released again, but now it's at depths where brittle failure gives way to ductile flow. The middle ground between them, the transition from stick-slip earthquakes to slow, steady creep, is where water shows its hand. In subduction zones like Cascadia in southwest Japan, geodesy and seismic networks record episodic tremor and slip, weeks-long, slow earthquakes that relieve strain without the sharp shocks of a magnitude 7. Their migration patterns trace pressure pulses diffusing along the plate interface. The agent that carries those pulses is fluid. Seismic attenuation helps pick out the wet zones. Beneath the forearc, waves lose energy faster than expected. That elevated attenuation, along with lowered velocities, lines up with regions thought to be overpressured by fluids. It isn't the same as seeing water, but it's a footprint consistent with it. Tiny films along grain boundaries, overpressured pockets at the base of the crust, channels in a ductile shear zone. When those pockets connect, the effective normal stress on the fault drops. With less clamping, sliding can begin at lower shear stress, creep, tremor, or a cascade that runs out as a moderate quake. On continental faults, the chemistry is different, but the physics rhymes. Deep fluids rise along fractures, altering feldspars and pyroxenes into clays like smectite and illite. Those clays are weak. A clay-rich fault gouge can host a seismic creep. A clay-poor one is more likely to lock until it doesn't. Changes in fluid pressure, seasonal recharge, injection, or natural pulses tied to deeper metamorphic reactions modulate frictional strength in real time. The system looks solid, but it breathes. Zoom out and you see a pattern, where plates are hydrated either by seawater at ridges and trenches or by deep source fluids along old suture zones. Deformation is distributed and often quieter. Where they're dry and cold, strain localizes until it snaps. Neither end member is safer. Quiet creep can load the lock patch next door. Locked stretches can go decades without a whisper, then rewrite a coastline in minutes. Water doesn't remove hazard, it shapes it. What about the mantle under the plates, the deeper engine? There, water is mostly in defects, not as free liquid, but its effect on viscosity is large. A few hundred parts per million of hydrogen in olivine can lower viscosity enough to alter how the asthenosphere flows. Softer mantle zones become channels guiding slab rollback and trench migration. Softer shear zones at the base of plates decouple crust from mantle, letting plates glide with less basal drag. Over millions of years, that changes where stress accumulates above. A hydrated asthenosphere is an invisible conveyor that shifts where mountains grow and basins sag. Electrical methods let us trace some of these pathways. Magnetotelluric transects across arcs and forearcs pick up conductive layers at the base of the crust and along the slab interface. Zones where fluids, melts, or hydrogen in defects boost conductivity above the background resistive mantle. Seismic studies add the attenuation map. Together, they outline corridors where fluids likely migrate. They also expose a hard limit. Conductors don't tell you pressure. A wet, low-pressure system can be as conductive as a wet, critically overpressured one. The difference between the two is the difference between steady creep and locked instability. That's why geodesy and microseismicity matter. They add motion to the picture. You can see the human stakes in places like Cascadia. Offshore, a broad, gently dipping interface shows tremor that marches along in 3-week waves every 14 months. Onshore, metropolitan corridors sit on soft sediments that will amplify shaking when the locked part of the interface breaks. In between, a conductive forearc channel suggests fluids are moving now, not just in the past. The deepwatercycle reminds you that the source of those fluids isn't only the shallow dehydration above the arc. It stretches down into the transition zone that feeds the wedge and modulates its strength. This is the grease you can't see. Water that changes the rules without announcing itself. It lowers friction where you'd want it to, until the patch that stayed dry decides to fail. It weakens rocks that would otherwise jam, redirecting stress into neighbors that weren't ready. It doesn't care about zoning or building codes. It follows gradients, reacts at thresholds, and keeps time on a clock longer than cities last. And yet, by listening for tremor, mapping conductivity, and tracking ground motion down to millimeters, we can watch the grease at work. We can't drain it, but we can learn where it pools, how it moves, and when a quiet slip is the sound of a bigger release preparing in silence. Iron, heat, and a planetary magnet with mood swings. Start at the center, where nothing we've said about water should matter, and yet it does. Earth's magnetic field is born in the liquid outer core, a shell of molten iron alloy convecting around a solid inner core. Motion of that conductive fluid, threaded by magnetic lines, sustains the geodynamo. It needs 3 things: heat to drive buoyant flow, rotation to twist it, and a conductor to carry current. None of that sounds like hydrogen in a crystal 500 kilometers up, but the core doesn't live in isolation. What happens in the mantle controls how fast the core cools, how it loses heat, and where. Heat leaves the core through the core, mantle boundary, like light through a stained glass window, unevenly. Above some patches, the lowermost mantle is hotter and sluggish. Above others, cooler and more efficient at wicking heat. That heterogeneity shapes core convection patterns. Over millions of years, it can strengthen or weaken parts of the geodynamo, shift the balance between stable and chaotic flow, and set the stage for the field's mood swings, excursions, and full reversals. Here's where the deep water cycle enters through the side door. Water in the mantle lowers viscosity. A hydrated asthenosphere is softer. It convects more readily. It organizes mantle flow differently. Water also lowers melting temperatures, changing how and where melt forms, which in turn modifies mantle composition and its ability to conduct heat. These are small levers, but over geologic time, they redistribute heat flow patterns at the base of the mantle. A wetter, weaker mantle can alter the shape and vigor of upwellings and downwellings, steering where slabs pool and where hot plumes rise from the deep. Those structures, cold slab graveyards and hot superplumes, sit right on top of the core and act as thermal throttles. Geophysically, we see the fingerprints. Seismic tomography maps 2 great low shear velocity provinces in the lowermost mantle, hotter, possibly compositionally distinct piles beneath Africa and the Pacific. Slabs subducted for tens of millions of years appear to accumulate around their flanks. Above slab clusters, heat extraction from the core is likely enhanced. Above hot piles, it may be muted. Add water's effect on viscosity higher up, and you've changed the plumbing that feeds these contrasts. You haven't touched the core, but you've changed the boundary conditions, it feels. Does that steer reversals? The honest answer is, it might nudge, but it doesn't push the button. Field reversals are chaotic outcomes of a self-sustaining dynamo. They've happened with different supercontinent layouts, with different slab fluxes, under different atmospheric chemistries. There's no evidence a single water release event flips the field. What's more plausible is a long time-scale coupling. Mantle structure modulates heat flux heterogeneity at the core mantle boundary. That shifts the dynamo's operating state. Sometimes the field becomes unstable enough to reverse. Correlation is not causation, and the timescales are glacial compared to a human life. But the coupling is real. The mantle sets the stage, the core improvises. Why should anyone outside a geophysics lab care? Because the magnetic field is a shield. It deflects charged particles from the solar wind and coronal mass ejections. When the field weakens, during an excursion or on the lead up to a reversal, more radiation can reach near Earth space. Satellites and power grids become more vulnerable to geomagnetic storms. The atmosphere doesn't vanish, but the operational risks rise. Airlines reroute, Astronauts shelter, high-latitude grids brace for induced currents. None of this is apocalyptic, but it's more than academic. Tie this back to the deepwatercycle and the ticking clock. Water's influence on mantle rheology and melting is a control knob on how heat moves upward. Imagine two Earths, one with a bone-dry asthenosphere, stiffer, shedding heat differently. One with a softly hydrated asthenosphere, more ductile, with different plume lifetimes, different slab stagnation depths, different thermal maps at the base. The core under each Earth would operate under distinct boundary conditions. Over tens of millions of years, their magnetic histories would diverge. Not because water changes iron, but because it changes the mantle scaffolding that the core feels. We do have ways to listen to this coupling. Seismic attenuation tells us where the mantle is softer and hotter. Magnetotellurics traces where conductivity is elevated by melts or hydrogen in defects. Together with velocity models, they map the mantle's ability to move heat, its radiators and insulators. Mineral physics constrains how much water phases can hold, so we don't overfit conductive anomalies with impossible hydrogen budgets. None of these tools reach the core, but they sharpen the map of the boundary conditions we hand to the dynamo. There's a limit we need to hold. It's tempting to turn every deep water story into a field reversal prediction. Don't. The link is indirect and slow. The same goes for fear of a sudden magnetic collapse tied to a volcanic decade. Short-term volcanic or tectonic bursts don't steer the dynamo. What they do through aerosols and climate feedbacks is challenge the surface. The magnetic field's challenges are separate and paced by the deep interior's long memory. Mantlewater likely modulates boundary conditions rather than forcing outcomes. Still, the connection matters because it reminds us that Earth is one machine. Hydrogen bound in ringwoodite melt along a grain boundary, a slab flattening at 660 kilometers. These are not trivia. They are the settings on the dials that control heat flow, and heat flow feeds the magnet in the dark. To see the stakes, though, we don't need to wait for a reversal. We need to watch what happens when deep water finds a fast route to the surface. When the valves line up, the discharge is not magnetic, it's volcanic. And when it's big, the sky tells the story. When rock boils, steam quakes in sudden lakes. When deep water finally joins heat on the way up, the rules flip fast. Magma doesn't need a lake to turn explosive, it just needs water to meet it, even as vapor or as hydroxyl leaving solution. As pressure drops in a rising melt, dissolved water exsolves into bubbles. Bubbles expand, link, and rip the melt apart. That shift, from liquid to foam to fragments, happens in seconds. Phreatomagmatic is the word, but the experience is simpler. Rock becomes steam-driven shrapnel. You see it in marked craters and tuff rings, those low rims around broad, flat-floored pits scattered through volcanic fields. In Auckland's monogenetic field, dozens of Mars record blasts where magma intersected groundwater. The magma doesn't have to be voluminous. What matters is the contact. Water flashing to steam expands by orders of magnitude, fragmenting melt and country rock, digging a crater that later fills with a lake. From the rim, it looks peaceful. In the moment, it's a pressure cooker that lost its lid. Yokolops tell a colder version of the same story. Beneath glaciers, ice-capped volcanoes melt hidden reservoirs against the bedrock. When a subglacial lake overtops a threshold or a meltwater tunnel opens, the drainage is sudden, hours to days. A valley that was a braided stream at breakfast can be a churning wall of water by noon, hauling boulders, grinding bridges. The eruption might be minor. The outburst flood is not. Water stores energy in silence. Release is the hazard. Hydrothermal systems do this on a small but deadly scale. Geyser basins and caldera domes are networks of fractures filled with near-boiling fluids under pressure. Seal a pocket with silica or clay, add heat from below, and the pressure climbs. A slip on a tiny fault, a drop in confining load after a quake, a clogged vent, and the seal fails. Steam flashes, volume explodes, and a shallow explosion crater scars the ground. No magma required. Afterward, the plumbing reconfigures, new vents open, and the clock starts again. What controls the odds is water content and pressure. The more water a magma carries, either from deep provenance or shallow assimilation, the earlier bubbles form as it ascends. Early bubble growth means faster acceleration and more fragmentation before gases can escape. That's why similar volumes of magma can behave so differently. One dome extrudes and pants for months. Another dome seals, overpressurizes, and shatters in a surge of ash and blocks. The difference is often water and how it moves between phases. Monitoring helps, but it's a race against hidden processes. Gas ratios at vents, H2O, CO2, SO2 shift as magma rises and degasses, giving hints about depth and saturation. Temperatures at hot springs creep upward. Chloride and silica concentrations change as reservoirs flush. Ground deformation swells and subsides as pressure cycles in the system. Microseismicity ticks like a Geiger counter when bubbles nucleate and pathways open. None of these predicts on their own. Together, they sketch a system walking toward a threshold. Lead time can be days for hydrothermal failures, months for magma-driven events, if instruments are there and the signals are read with caution. Here's a micro-story that researchers tell in quiet tones. A field team was mapping altered ground on the flank of a restless caldera. They paused at a steaming terrace as the wind dropped, and the ground made a sound, like a giant sleeping animal, slow, deep breaths. That was the cap rock flexing over a pressurized pocket. They backed away. 2 days later, a hydrothermal explosion tore a crater the size of a house through that spot, hurled mud and rock 100 meters, and coated the surrounding pines. No warning siren, just pressure finally exceeding strength. Not every dramatic change needs an eruption. When rising magma or hot fluids intersect an aquifer, you can get sudden crater lakes where none existed, then equally sudden draining when a throat opens to a deeper level. The shoreline stains tell the story. A bathtub ring of iron and silica dropped meters in a night. On maps, these are shrugged off as ephemeral. If you're downstream, they are anything but. The chain reaction is physics with an attitude. Water holds an enormous latent heat of vaporization. When it flashes, it soaks up heat and expands, driving fragmentation that exposes more hot surface, which accelerates flashing. A feedback that builds in a heartbeat. In confined spaces, that feedback fails only when the cavity has vented or the pressure source has been cut.